Welcome to Akool Research Publications. This paper presents a novel energy-based cooperative learning framework for multi-domain image-to-image translation. The task of image-to-image translation primarily involves the learning of mappings between different visual domains. This learning framework carries immense application value in the field of generative artificial intelligence, facilitating the development of various creative products for artificial intelligence-generated contents. An ideal image-to-image translation framework should possess the ability to handle multiple domains, efficiently process high-resolution images, and provide diverse synthesis when translating to each target domain. While several pioneering works have made significant strides towards this goal, it is noteworthy that they predominantly rely on adversarial learning techniques. In contrast, this paper explores the multi-domain image-to-image translation problem using energy-based modeling techniques. This research is motivated by the current swift advancements in energy-based modeling and learning technologies. The framework consists of a style generator, a style encoder, a translator and a descriptor. The first three components, that is style generator, a style encoder, a translator, form a diversified image generator. Given an input source image, the translator can transform it into a target domain, which is specified by a style code. The style code can be obtained by sampling from the domain-specific style generator or extracted from a reference image by the style encoder. The descriptor is a multi-domain image distribution, which plays the role of guiding the translation such that the translated images can match the observed images in the target domain in terms of statistical property. All components are trained simultaneously in a cooperative learning scheme. The descriptor learns from the multi-domain training images by maximizing the data likelihood, while utilizing MC teaching to guide the training of the diversified image generator, which includes the translator, style encoder, and style generator. The cooperative learning alternates the maximum likelihood training of the descriptor and the diversified image generator. We first present the loss of our descriptor, which is a multi-head energy-based model. Its loss contains a regular constative loss and an L2 norm regularization term. The constative loss is derived from the maximum likelihood estimation, and it requires Markov chain Monte Carlo samples. The L2 norm regularization term is added to increase the stability of the energy-based training. We then present the loss of the diversified image generator, which include the style encoder, style generator and the translator. The loss includes an MC teaching loss, which is required for the cooperative learning, a diversity loss, a cycle consistency loss, a style code reconstruction loss, and an energy-based regularization on the translator, which aims at shifting the translator mapping toward the low-energy modes of the energy function. Our framework uses multi-head for each component, so that they can represent multi-domain knowledges. Also, to significantly improve training efficiency, we propose a progressive learning strategy for our cooperative learning framework. The algorithm gradually enhances the model resolution from low to high, while maintaining cooperative learning across all components at each resolution. The underlying motivation behind this strategy is that learning and sampling from a low-resolution data domain is much more efficient. By leveraging a pre-trained low-resolution model as a foundation, we can efficiently learn the next scale of the model, rather than starting from scratch. When expanding the current model to the next scale, each component's network structure undergoes modifications. New layers are added to handle higher resolution image inputs or outputs, while incompatible old layers are removed. The newly added layers are trained together with the remaining parameters. Now we are going to show some results. We first show the translated images with style codes generated from the style encoder and reference images in Celeb A, HQ dataset. The source images and reference images are put in the first row and first column. We can see that the face has successfully translated into the target domains with consistency in expression and head poses. This is another set of examples to show results in animal dataset. Again, the source images and reference images are displayed in the first row and first column respectively. We can observe that the animal faces are successfully translated into the target domains, while preserving the original face geometric structures. We then use style codes that are randomly sampled from the style generator to generate diverse translated images. Examples of generation results on the Celeb A, HQ dataset can be seen in this figure. For each source image shown in the first row, we generate multiple outputs using random Gaussian noise. The qualitative results verify the diversity of the translated results from a source input image, as well as the expression-preserving capability of the model. Here is another set of examples of diverse image-to-image translation, which is performed on animal dataset. The first row shows the source images. For each source image, we generate multiple outputs using random style codes. We can see that the translated images not only show diversity but also consistency with the source images in terms of the geometry. To verify the cycle consistency of the model, we conduct experiments for cycle image-to-image translation. Firstly, we perform an image-to-image translation from the source domain to the target domain, guided by a reference image. Then, we reverse the translation by taking the translated image as the new source image and translating it back to the original domain. The qualitative results clearly demonstrate that our model exhibits excellent cycle consistency properties. It effectively preserves the geometric features of the source image while applying the appearance properties from the reference image during translation in both directions. These are the results for verify the cycle consistency on the animal face dataset. This table presents a comparison of different models for image-to-image translation in terms of FID. A lower FID indicates better quality translated images. The model is comparable to the adversarial training framework, such as StarGone 2. We briefly summarize the paper below. This paper proposes a novel energy-based cooperative learning framework for multi-domain image-to-image translation. We build a single multi-head energy-based model to represent probability distributions of multiple domains, and train it with a translator, a style encoder, and a style generator using a cooperative manner. The paper presents a novel progressive learning algorithm to optimize the training efficiency of our framework. This paper proposes regularization strategies to stabilize the cooperative learning, which include an energy-based regularization loss for the translator and an L2 regularization loss for limiting the magnitude of the energy values of the descriptor. The method obtains state-of-the-art performance among existing energy-based image translation models and comparable results with GAN-based baselines. Thanks for your listening.